All right, it's 1 o'clock. Hey, everybody. So today we're going to be practicing hydrogen NMR and how to interpret it. We're going to dabble in a little bit of carbon NMR today, since that will be on your quiz on Wednesday as well. In lab today and or tomorrow, whichever day you have lab. Hey, don't forget that you're all coming to lab today or tomorrow. And so it doesn't matter what you wear, because we're not going to be in lab. But we're going to be practicing IR, mass spec, NMR again today. That's what we'll be doing in lab. So just be ready to have your thinking caps on and spend like 2 straight hours practicing, or 3 hours NMR, mass spec, and IR. But for today, we're just going to go through some spectra. I'm going to kind of help the best I can without being overbearing. The best way to practice this is really just to commit to building those pieces and practice putting it together. Like I told everybody on Friday, there is no one best way to build a puzzle. So it's largely up to you. And so it's kind of a skill that you practice, and after you practice enough, you get good enough to be able to do it. But number one, you definitely need to be able to build your pieces correctly. So I went through and graded all of these bridges, not graded them per se, but gave you feedback on them and looked at all of them. And the biggest problems that went on were puzzled, like the pieces, the signals being interpreted incorrectly. We spent a bunch of time on that last week. That was all we did last week. It's the same information, so it's not new now. So just go back to those if you need to. Let's go through these 3 peaks one at a time. Looking here, I'm going to label these as, we'll just call them A, B, and C. So there's only 3 peaks. So there will only be 3 different environments in your NMR for hydrogen total. So if you had more than that, if you ended up with a bunch of carbons and a whole bunch of extra hydrogens in the product, that definitely can't be the product. These can be the only hydrogens in the molecule. All right, so looking at what we've got, basically questions A, B, and C, we're just interpreting those 3 environments, A, B, and C. So looking at that first one, you can probably tell that that's a doublet, pretty clearly a doublet. C is also a doublet. It's pretty hard to interpret how many signals there are on B, and so that's why I gave you that it had 9 peaks. But let's start with A. It integrates to 2H, which means that it is a CH2. Much like I harped on everybody on Friday, I would circle that environment, maybe even do this, so you know what you're looking for, because this is the environment that's accounted for. You will know information about the neighbors, but those neighbors will have to have their own signals. So this signal right here, this doublet at A, is telling you about this environment right there. It gives you more information, but that's the one that it's counting for, and we have to put into our product. All right, it's around like 2.9 ppm. So it's not perfectly clear, because it's not 3 to 4 and it's not 2 to 2.5. So what we can say for sure is that it's a doublet, and a doublet definitely means that it's next to what? Okay, so what is it next to specifically? Right, so it's got to be next to a CH. Besides that, what do you think is on the other side? Got a lot of different answers for this. Right, so it's a little tiny bit lower than we would expect for O or N or an X, but it's pretty close. And it's definitely higher than 2 to 2.5. So it could be a carbon-containing functional group. But it's definitely closer to 3 to 4 than it is to 2 to 2.5. But it's impossible to say for sure. But it's definitely next to something. So I'll just put it all in there for now, because we don't really know. It's definitely next to something. Does that make sense? All right. Let's move over to that central one. This one has the most information right here. It integrates to 1, so it is a CH. And it has 9 peaks. So the integral is going to be clear and for sure. The splitting is going to be clear and for sure. The chemical shift is something that there's a lot of ways to justify it. But 9 peaks, what does that tell you? Right, and how could we do 8 hydrogen neighbors? There's only one way. Yeah, it has to be 2 CH3s and a CH2. All right, it is right around 2 ppm, but could it also be next to a carbon-containing functional group? How many bonds does carbon make? 4. So it's got an H, it's got 3 carbons, because that's the only way it's going to have 8 hydrogens. So can it have any more bonds? No. So can it be next to a carbon containing functional group? No, because it's got everything. So how could it be 2 to, or I guess 1.5 to 2? Yeah, it's basically got to be 2 doors down from something. We wouldn't know what, but to be that high, probably an O or an N or an X, but still it's got to be 2 doors down from something. But it can't be right next door to anything else. Right, so this is our environment B. C, at this point, if we've been going in order, hopefully our context clues can help us on that. We've accounted for this CH2 right here. We've accounted for this CH right here. So the only thing left is 2 CH3s that we haven't accounted for yet. So you could start from scratch and we could do that. But I mean, we've done these two. We may as well, you guys are adults. You can hold a little tiny bit of information in your memory there and look down and say, well, we already have 2 CH3s to go. That would integrate to 6. So it's probably those 6 H's. You can do all of these alone in their own little boxes, but if you start going through them, feel free to use the information you have already to do the rest. But this is 2 CH3s since it integrates to 6, and it's a doublet, so they're next to a CH. So logically, it's those 2 right here, but we'll go ahead and write them out. It's 2 CH3s, both of which are next to a CH. So by circling them, I can see that I have a CH2, a CH, and 2 CH3s, and that's all the hydrogens I have in the molecule. Everything that I've written in terms of CH2s and CH3s and CHs that's outside of those circles, that tells us about our circled part's place, what it's near. But we don't have to have a CH2 and a CH and another CH2 and another CH and 2 more CH3s and a CH and 2 more CH3s. Right. The ones that aren't circled are just peripheral information. All right, so when we put all of this together, we would have, I'm going to start at B. I've got that environment B, and that's a CH next to 2 CH3s. I'm going to have those 2 CH3s next to it. Those were environment C. And then that CH also had a CH2 to the left, which must be this one, environment A. And then there's whatever else. So for that whatever else, we don't know for sure what it is, but we do know that there are no more hydrogens in this molecule. So it can't be an NH2, and it can't be an OH, and it can't be a benzene ring or an alkene or an alkyne, and it can't be a carboxylic acid or an aldehyde. So there's not a lot left of our O/N/X/ carbon containing functional group. So what do you think it probably is of those options? Yeah, halogen probably. You say bromine? I'm sorry. What did you? Okay, so carbon. I'm sorry. I thought you said bromine. And I wasn't sure. So what carbon containing functional group could it be? The problem with carbon containing functional groups here is that most of them have a hydrogen, at least one. So it's possible. It could be a C triple bond N, because that would have no more hydrogens, and you would have a carbon and a nitrogen and a carbon. So that could make sense. What else? It could be a halogen. It's probably not an O, because that would probably have an H. It's probably not an N, because that would probably be an NH2. So probably it's a halogen and maybe a carbon containing functional group. I mean, technically it could be an oxygen with this thing on both sides. But you wouldn't know for sure unless you ran some other spectroscopy. So this is what we would know for sure. I'm going to say probably a halogen. And the answer is it's a chlorine, but like you wouldn't know that for sure. So what could you do to figure out what that is? Yeah, so mass spec would definitely tell you. IR would tell you if you had a nitrile or some other carbon containing functional group, because those show up pretty well. But you'd have to do something else to determine specifically what else was over there. But this part we could do for sure using our hydrogen NMR. And that's what hydrogen NMR is primarily good for. It's telling you about the carbon-hydrogen framework of the molecule. It's not perfect for functional groups, although it gives you some information. but this is what it does, and it did it well. All right, any questions on this bridge? All right, then let's move into the rest of that sheet that you guys printed out on Monday or Friday. We did the first 5 pages of this together. And so the rest of this is 5 more hydrogen NMRs, and some of them have a carbon NMR asking you whether or not your answer to the hydrogen NMR fits. So we're going to focus first on the hydrogen NMR, and I'm going to give you just a little bit of information on this and then just give you time to work on it yourself. All right, so this is 4 environments. We should definitely be doing that same thing. This would be environment A, B, C, and D. I will give you the integrals on your NMR. I've written them down below here from left to right. But this one is 2H, 1H, 2H, and 3H. Can you tell what the splitting is? What's that first thing? Yeah, so that's a 2H triplet. All right, what's this one? B. What? Yeah, it's a singlet. It looks a little bit broad and weird, so take that information. It can be helpful, but it's a singlet. This one here, you can kind of count if you look really closely. 1, 2, 3, 4, 5, 6 peaks. And then this last one is a triplet. Hopefully you can see it's kind of a 1 to 2 to 1. So this is a triplet. All right, so go through and account for each of those pieces and put them together, but I will give you, let's talk about B real quick. It's a 1H singlet. What are 1H singlets almost always? OH or NH, right? And you have an oxygen. So I would be pretty certain that B is an OH. All right, I'm going to give you some time to go through and try to do this one on your own. Ask me if you have any questions. If you're in Zoom, just yell, I can hear you. I might be walking around in this room, but ask me if you have any questions. Today is going to be probably too slow for some people and too fast for other people, just right for some people. But by all means, keep going. What's that? Yes. That'll make that much better. He's an OH, not a CH. So environment A is between 3 and 4 feet. So in this case, we know there's an O, we know there's not a P, we know there's not a hydrogen C. And then it's also a triplet. So this gives you a good amount of molecules, you know. No. That carbon right there has lots of names. 5 bonds. Just move, you got the right thing, so it's not attached to the correct way. Yes, yes.
So is this,
Yep, okay.
okay, so these are gonna be the same, so that's just them.
Yeah, so before we do anything, we would say it's next to an O or an N. But because we know there's an OH in here, it has to just be. All right, so let's go through this one together. And if you feel good about it and you've got it right, feel free to be moving on. But environment A is a 2H triplet. 2H meaning it's definitely a CH2. A triplet meaning it has 2 hydrogen neighbors. So at this point, we wouldn't be clear if it had 1 CH on each side or a CH2 on one side. But because it's between 3 and 4, it's definitely got to be next to that oxygen. So it's got an oxygen on one side. We would say O or N or X, but in this case, you have the molecular formula, and you know there's an oxygen, no nitrogen, and no halogen. So it's got to be that, which means that the 2 hydrogens would have to be on the other side. It's got to be next to a CH2. So this is our environment A. We already talked about B. It's got to be an OH since it's a 1H singlet, or it's very much most likely an OH since it's a 1H singlet. Environment C integrates to 2, so it is a CH2. It has 6 hydrogen neighbors, and the only way to do that is to have, it's got 6 peaks, so 5 hydrogens on neighboring carbons. It's got to have a CH3 on one side and a CH2 on the other. So this is your environment C. And then finally on the far right, we have a 3H triplet, which is a CH3, Triplet means it's got 2 hydrogen neighbors, so it's next to a CH2. So I kind of lined these up so that you could see that connection. We've got an OH as kind of our first position, and then that's next to a CH2, which is next to a CH2, which is next to a CH3. You've got all of that stuff, and it's just all in a row. I would also tell you that if you look at what you've got here, you got an OH, which has to be at the end since it only makes 1 bond. You've got a CH3, which has to be at the end because it only makes 1 bond. All right? And these are both CH2s, which have to be in the middle because they make 2 bonds. And really, just looking at those integrals, there's only one way to put that stuff together, kind of like a train. You got one thing at one end, one thing at the other end, and then just the CH2s in between. So sometimes you can kind of work your way to these without having to worry about every detail. But I think focusing on the details is a really good thing, especially when you're first learning how to do it. So these are our peaks. All right, real quick carbon NMR question. What would the carbon NMR of this thing look like? I will never ask you to draw a carbon NMR. I will either ask you, does this work with yay carbon NMR, or this carbon NMR which fits best which of these molecules? But Sydney, how many carbon environments would you have? 3, correct. Caleb, where would this one be? Next to an O. Do you remember?
That would be kind of like your upper inlet.
So in carbon NMR, the whole scheme is shifted. So these two right here, how about this question? These two right here, where would they be? They're kind of not next to anything. If you don't remember the numbers, it's okay. So just thinking about carbon NMR, you kind of got that farthest to the right is just alkanes. And then next is the stuff next to O or N or X. So these guys are just farthest to the right, like 0 to 35-ish, but farthest to the right is fine. This guy A, which is next to an O, it's probably in that kind of second quartile over, probably around like 60 to 90. So it should look kind of like this, boop, boop, boop. That's about it. So you will have that on your quiz. I will break my heart if you do all of this complicated stuff correctly and then you get that one wrong. But do review that a little bit. Don't forget that that's still a thing. All right, so this is the next one. Give it a try. Let's go ahead. I'll just label these A, B, and C. And integrals are 1H, 3H, and 6H. You will have to use some logic to deduce what's in there. You should have 5 carbons, 10 hydrogens, and 1 oxygen at the end of the day. It is 7 peaks. That is not something I would expect you to notice, so that's I labeled it in there. I will label that on your quiz since you can't zoom in yourself. So there is a CH there. Right, just be aware of this. And then this one is the CH. What is it? 7. That's 7. A and C are kind of telling the same thing. Right? Yes, exactly. But there's not two of these lines that over, there's only one. It's just that this is talking about CH, this is talking about exactly. Perfect. Why are you saying this? You write it into something. I would make the case that this is close. You know, this is really short. What do you think is more than? What puts you in that 2 to 2 point factor? Yes. So you do need to figure out what that is. Okay, what's up?
So these are all CH3s.
Yep.
Does something have to like split it?
Yes. So
So
something's
that
in
it's part of the functional group that's split the last.
Yes. Yep. So based on the fact that you have 5 carbons, 10 hydrogens, and 1 oxygen in the molecule, what does your carbon containing functional group have? An oxygen and what else? Yep. So what carbon containing functional group is carbon on?
Double bond, right?
Yep, perfect. You got it. Oh, well, why angle structure? We haven't drawn those in a minute. Does that all make sense? Oh, so you have a CH3 in there. This is good. The CH next to 2 CH3s. This is your 2 CH3s, and they're doublets. What is that? Yeah, so the way you have it on here is perfect. This is environment A, and that's environment C. So, it's all right. It's okay. You've got the right information here. And so that's next to something, and then you've got CH3 on the top. Okay, that's the CH3. So what is this thing? Right. So what are we missing? We haven't. The CH3 is definitely over here. You can tell that's- Yeah. So it's going to be some carbon containing functional group of milk, which contains an oxygen and then one other atom. This is C double bond. Because we've got 4 carbons now. 4, 1, 2, 3, 4. That should be 5. Let's see.
Thank you.
You're welcome. That's perfect. Almost perfect. All right, so it's not an aldehyde because that carbon would be making 5 bonds. And you have a peak between 9 and 10. So it's just a C double bond. C double. And then where's your other? You knew that was a CH3.
Yeah.
So that's it, and that's perfect. That's it. Good job. All right, I think everyone in the room has this, so we're going to go through it for the people in Zoom. If you want to stick with me here, you're fine. If you want to move on and keep working on those, that's fine too. So environment A, right here is a 1H with a lot of splitting. I told you that a 1H singlet is probably an OH or an NH, but a 1H with a bunch of splitting is a CH with neighbors. So this is a CH, environment A, and it has 7 peaks, so it's got to be next to 6 different hydrogens on neighboring carbons. There's a lot of ways to do that. It could be two CH3s or 3 CH2s, but just looking in here, you see that we have this 6H doublet, that's 2 CH3s. And furthermore, this thing is around like 2.6 ppm. So it's probably next to a carbon containing functional group on one side. And both of those go together to tell us that it's probably just 2 CH3s that it's next to, and then a carbon containing functional group. And that's its 4 bonds, so that carbon's pretty good. We can skip on down to C. This is our 2 CH3s. A doublet means it has 1 hydrogen neighbor. So these are 2 CH3s next to a CH. That's your environment C. And then, of course, you can see that this A and C are 2 ways of looking at the same story, this little isopropyl group. This is the CH with the CH3 neighbors. This is the CH3s with the CH neighbors. So those just go together. And then B is just a 3H singlet. So it's a CH3 with no hydrogen neighbors. It's around like 2.1 ppm-ish. The number exactly doesn't really matter. We're just looking at regions for these anyway. So it's probably also, we would guess, next to a carbon containing functional group. So at this point, what we've got is kind of this thing, a CH3 and then some carbon containing functional group, and then a CH and 2 CH3s. This is your environment B, A, and C. All right, so looking at our molecular formula, we should have 10 hydrogens, which we've got, 3, 6, 9, 10. We should have an oxygen, which we're missing. We should have 5 carbons. We've only accounted for 4, so we're missing 1. So we have a carbon and an oxygen that must be in our carbon-containing functional group. So just by process of elimination, this isn't just some random CCFG, it must be a CO. And the only way to make everybody have the right number of bonds is a ketone. So if we had run IR first, we would have known there was a ketone, and that would have made our job a lot simpler here. We wouldn't have had to figure anything out, but we could figure it out without that. And so that works, and that's the only thing we've got here. In a carbon NMR, where would this carbon show up right here? Savannah, where would a carbon and a carbonyl show up? You remember? Yeah, all the way to the left. So if you're looking for numbers like above 150, but all the way to the left is perfectly fine, kind of the leftmost quadrant. All right, and then the rest of those should just be all the way to the right. There would be 3 more carbon Bs. All right, good job. So any questions? You guys kind of see the process? This one, third one here, looks really weird and tricky because there is no splitting. But a lack of splitting tells you a good amount of information. So go for it. It's only 2 peaks. No, this is just a true false question. This is correct. So does that make sense? No. It is correct. It's an aldehyde. Let's see the one. Always have to be. We can't do that in each other, or else we can split things. Right. So they're not made of anything. So what do you think 9H is?
Well, first I was like, we're gonna see which one is
Right,
correct.
yes. That's correct.
That's correct.
It doesn't mean they're attached together, just that they're in the same environment. All right, how many meters do they have? Hydrogen.
Okay.
No, it's a single.
It's nine.
No. So they have to be attached to a carbon with no hydrogens. So draw a carbon with no hydrogens, and you get a 3CH3.
According to the CH3.
Yeah. So then all three of those CH3 would be identical. They're all next to a carbon with no hydrogens.
Oh, that's the fifth carbon. Yeah.
A lot of these make sense when someone tells you what they are, but that's that's really the only way to do 3CH3s that are identical is have them all attached together. Perfect. Is this it? It's okay. Good, that's right. Yeah, that's perfect. Yeah, that's it. All right, so we don't always see these 9H peaks, but hopefully logically you guys in Zoom got to this. If you see a 6H, it's 2 CH3s. See a 9H, it's 3 CH3s. They're all identical and they're all next to a carbon with no H's. So most likely, and in this case, definitely, since you only have 5 carbons in the molecule, they're all next to the same carbon. So this is all environment B. And then this is an aldehyde, environment A. It's a C double bond O with an H. And that's your environment A. And so that's it for the molecule. Here's 5 carbons, 4 and 1. Here's 1 oxygen, and then there's 10 hydrogens. So it just must be attached to it like that. Well, that's everything. That's how it goes together. Looking at our carbon NMR down here, this is basically a true false question. Does this molecule, or this carbon NMR, fit this molecule right here? All right, Olivia, what do you think?
So the C double bond to an O shows us at all the way to the left.
Right, so kind of up in this region.
Yes. So, no.
Correct. So this one, if this was right, you'd have 1 peak up here and then 2 peaks over here. Anybody remember what these things are? Kind of the 60 to 90-ish? Yeah, so these are probably carbon with a single bond. Carbon's right next to it. And so whatever this is, it maybe looks like an ether or something like that, but it's definitely not that. All right, we've got 20 minutes left and 2 more molecules. So I can do the math on that. Go at your own pace, but we're going to take a pause in about 8 minutes and go through this one right here, the 9th one. And then at the end of class, we'll go through this final one as well. Can you guys make out the splitting on these? Yeah, so this is a quartet. You see it kind of goes boop, 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 boop. And that's a singlet. And this one's a doublet. It's just 2 beats. And this one that's splitting is just kind of a mess. But when you're between 7 and 8 ppm, it doesn't really matter. You can figure it out without the splitting.
It's kind of nicely colored, but it's also even higher than that, so it's probably next to it. See that light? Lights in there, which is great, honestly. See if that would use. That's something that's better. You were working towards a way to figure out the carvings. It just ends up. You can see this. So when you see that, which we've seen a couple times already, it's down here somewhere. I would see what it's at. So otherwise, it's like it's really hard to account for. That shouldn't be there. There is no double bond. Note this is getting close to 5. This is just, it integrates to 1, so it's a CH. It's probably next to a couple different things.
Okay.
It would be 4 different carbon.
This is what equal that?
Yeah, if it's got something on this end, then this would be 1 carbon, those would be the same, so B, C, and D would be 4 carbon.
Is it right equal to this one, or is it the other one? Or the other? One, two, three.
All right, we're going to take a pause and go through this one together. Just a quick reminder, your quiz will be 1 hydrogen NMR, 1 carbon NMR, and you'll have 30 minutes. So today, we're trying to kind of do these in like 10 minutes. I'm making you go a little faster. When you're doing it by yourself with no notes and for your quiz, you will have sufficient, hopefully sufficient time, but significantly longer than I'm giving you right now. So looking at these guys and going through them one at a time. For sure, A is a benzene ring, since it's between 7 to 8 ppm. It has 5 hydrogens on it, which means that since benzene always has 6 spots, you have 5 spots with hydrogens and 1 spot with the rest of your molecule. So you can kind of think of this thing as being at one end of your molecule, since it only has, it's basically a dead end. It's got 1 spot for things to come up. So this is environment A. Your environment B is a 1H quartet. So it definitely is a CH, since it's a quartet. It has 3 hydrogen neighbors, and the way to account for that would be a CH2 and a CH, or a CH3. You can tell that you don't have any CH2s anywhere, so it's just got to be a CH3. So it's got to be next to a CH3. Furthermore, it's above 4 ppm. So we can't say for sure what it's next to, but it's got to be at least next to that oxygen. Probably the oxygen and something else. Does that make sense? So you can try to account for everything in here, but it's got to be the oxygen, probably some more. That's probably enough for us to say there. Anytime you have a 1H singlet, I want your brain to tell you NH or OH. So we'll just go with OH here, since we know we have an oxygen and we know we don't have a nitrogen. All right, lastly, we have a CH3, since it is a 3H. It's a doublet, which means it has 1 hydrogen on a neighboring carbon, so it's next to a CH. So these two right here go together. There's your CH next to a CH3, and there's your CH3 next to a CH. So this is environment B, and that's environment D. And we could just kind of jot those out together. So we've got a CH in the middle. We've got a CH3 on one side of it. So that's environment B and D. And we've got our OH, but if you look at this, we only have 2 more things. We've got our OH and we've got our benzene ring. And this little chunk here only has 2 spots for stuff. So it's got to have the benzene ring on one side and the OH on the other. And that's the only way to put all this stuff together. And it adds up to be all of your correct number of carbons and hydrogens and your 1 oxygen. All of those guys are A. This guy right here is C. So that's your molecule. It's a benzene ring with a 2 carbon chunk, and OH coming off of the first one. All right, looking down here at this carbon NMR, Our molecule again was a benzene. I'll just do a line angle structure of this. So it should have 1, 2 carbons and then a benzene ring. A benzene ring in this case is going to count for 4 environments. It would be 1 right here, 1 right here, and then these 2 would be equivalent and these 2 would be equivalent. So it'd be 4, 5, 6 peaks. So just based on that, this doesn't work. Because this is 1, 2, 3, 4, 5, 6, 7, 8 peaks. Furthermore, your carbon next to an oxygen should be the 60 to 90 and you have nothing there. So there's a lot of reasons why this one also does not work. All right, 1 more to go. All right, we got 7 minutes left in class. So I'll give you a quick couple minutes and then we'll go through this one together. Kylie, tell me what you think about A. Oh, which one did you do? Okay, so tell me about C. Okay. Perfect. That's a CH3 next to a carbon-containing functional group. All right, and we'll work out what that is in a minute. Sydney, tell me what you know about B.
It's a CH2.
Okay.
And it's not next to any hydrogen.
Right.
Around 4.5 ppm.
Yeah.
So, maybe it's next to the BR.
I think that's a perfectly logical thing for it to be next to. So the bromine would probably pull it up to like 3 to 4. So what would you deduce is on the other side?
A carbon containing functional group.
Great, great. All right. Caleb, what's this thing in A? It's a what? We just had one of these on the previous one. Anytime you see those peaks between 7 and 8, what is that thing called? Right, it's a benzene ring. And the benzene ring is a carbon-containing functional group, which kind of answers the question from the other ones of what's the carbon-containing functional group. So if you started with this one, you'd have your carbon-containing functional group already, but it's okay, you would have gotten there. So we've got a carbon-containing functional group. Olivia, how many hydrogens are on it?
3.
So the quartet tells you neighbors. What tells you about how many hydrogens are in? 4, yes. So there's a couple different ways to put 4 hydrogens on a benzene ring. But because you see this is so symmetrical, it probably means that your hydrogens are symmetrical as well. So most likely, the hydrogens look like this, where the whole thing will have something on the right and something on the left. All right, so Savannah, where'd you put things? Did you get very far? That's okay. We're gonna have on one side a CH3, which was our environment C. And then on the other side, we've got Sydney's little chunk, which was a CH2Br. And I don't think 2 minutes is nearly enough for you guys to put that together. But this accounts for all of our stuff. So that's everything right there. So what this should look like in a carbon NMR is you'll have one peak way to the right, one peak kind of middle-ish right, like maybe 30 to 60. And then you should have 1, 2, 3, 4 carbons with kind of mid-left around 150 plus. When we look at this, that's exactly what we've got. This is a carbon kind of near nothing, which is what we have. This is a carbon that could be next to a halogen, which works. And then this looks like there's only 3 environments here, but I zoomed way in, and I told you this right here. There's 2 peaks that you can't decipher. I mean, if you zoom in, you can tell that there's 2 almost right next to each other. So this works out that there are 4 carbon environments in a benzene ring, and one of them next to a bromine, and one of them just off in its own space. So yes, this one does actually work. All right, any questions on this? This is a lot, and this is not a simple thing to do. It takes practice, so we should practice. That being said, I will see you guys in lab either in 17 minutes from now, or tomorrow morning, or tomorrow afternoon. If you are in lab today, we'll be meeting over in 222, so you don't have very far to go. Tomorrow morning, we will be in the conference room, and tomorrow afternoon, we'll be in this room. So whichever one you're in, we'll have a place to go. Thanks. I will see you today or tomorrow.